Welcome to this explainer. Right, let's jump straight into this. At first glance, a rolling element bearing looks, well, pretty straightforward, doesn't it? Just some metal balls or rollers spinning away inside a ring. But honestly, that seemingly simple shift from sliding friction to rolling friction introduces some absolutely massive engineering stakes. Today, we're zeroing in exclusively on rolling element bearings. We're going to decode the strict mechanical rules and procedures that dictate whether a machine runs flawlessly for years or literally destroys itself in a matter of hours. Here's our roadmap for the session. We're going to breeze through the principles of rolling contact, move on to assembly design and tolerances, hit the strict rules of maintenance, look at essential tools and gear, and wrap it all up with precision mounting procedures. Section 1. Principles of rolling contact. Let's look at the core concept here, swapping out that old sliding action for rolling elements. Now, unlike sliding mechanisms, these bearings stick a series of rolling elements, your balls or rollers, right between two moving surfaces. And because we're rolling instead of sliding, the material requirements completely change. The elements and the raceways they travel in, they absolutely must be made of specially hardened steel. Why? Well, the harder the elements, the less the surface deforms, which drastically cuts down frictional resistance. But here's the real kicker. That hardened steel is crucial because the actual contact areas are incredibly tiny. I mean, think about it. With ball bearings, all those forces are concentrated on a microscopic point of contact. With roller bearings, it's focused along a very thin line. And because that load is squashed into such a minuscule space, the lubricant that gets dragged into the contact area is put under immensely high pressure. Surprisingly, this actually forces the viscosity of the lubricant to spike, massively increasing its load-carrying capacity exactly when and where it's needed most. This matrix here brilliantly shows how engineers manage all those intense forces out in the real world. Think of it as the ultimate cheat sheet. It breaks down exactly which bearing type suits which specific demand. So are you dealing with purely radial loads, purely axial loads, or maybe a combination of the two? Whether you need a deep groove ball bearing for crazy high speeds or a spherical roller bearing to handle really heavy combined loads, hitting the nail on the head and matching the exact right bearing to the physical forces of your machine is step 1 for success. Moving on to Section 2, Assembly Design and Tolerances. So how on earth do we keep a bearing perfectly locked onto a spinning shaft without completely crushing it? The main trick we use to secure a bearing is an interference fit. And let me tell you, this is a seriously tight fit. You can't just push it on by hand. You're going to need a press, a driver, or some thermal expansion through heating to get it installed. As a golden rule in mechanical design, the rotating ring of the bearing, which, is usually the inner ring on the shaft, gets this interference fit. This ensures it stays completely locked in place while it's spinning under heavy load. On the flip side, we have the slip or push fit. Just like it sounds, this fit is loose enough that you can literally just slide it into place with your hands. We typically use this on the stationary ring of the bearing, which is mostly the outer ring sitting inside the housing. Not only does this make assembly way easier, but crucially, it allows the bearing to make those tiny, microscopic adjustments during operation. And that floating setup, it solves a massive real-world physics headache: thermal expansion. Look, when machines run, they get hot. And when metal gets hot, it expands. If you've got a rotating shaft held by two bearings and both of them are locked down completely tight, well, the thermal expansion of the shaft is going to physically crush those bearings. No way around it. So the assembly has to be designed with one bearing securely held in its housing, whilst the other is left floating as a non-locating bearing. That way, it can move just a fraction to absorb all that axial growth. To keep everything in its exact axial position on the shaft, we rely on some specific mechanical locking devices. The most common setup you'll see for both single and double row radial bearings is a specially designed shaft nut paired up with a locking tab washer. Now, for parts like the inner cones of tapered roller bearings, you'll often spot a slotted or castle nut secured with a split pin. Basically, these devices are there to guarantee that all the vibration and rotation doesn't cause the bearing to just wander out of position. Okay, Section 3. Strict rules of maintenance, because, let's be honest, all that brilliant engineering we just talked about can be entirely ruined by one simple human error. When you are handling rolling element bearings, you genuinely need to adopt a surgical level of cleanliness. We're talking completely free of dust and dirt particles at all times. You've got to handle them with strictly clean, dry hands or fresh gloves. Not using them right away? Wrap them up in oil-proof paper. And please, don't use dirty cotton waste to clean them. Stick to clean solvents and lint-free rags.
Oh, and here's perhaps the most common fatal mistake. Never ever spin a dry, unlubricated bearing with compressed air. Doing that can cause instant scoring. You'll literally ruin the component before it even makes it onto the machine.
This brings us to a massive, absolute rule. We call it the force rule. Whenever you're mounting or dismounting a bearing, the physical force must always be applied to the ring with the interference fit. Never, under any circumstances, apply force in a way that transmits through the balls or rollers themselves. If you smack a bearing directly with a hammer or force the outer ring to try and push the inner ring onto a tight shaft, those rolling elements will physically indent the hardened steel raceways. It's irreversible damage. Game over. Right. Section 4. Essential tools and gear. Because of that strict force rule we just discussed, raw human power just isn't going to cut it. You absolutely need specialized mechanical gear to handle these components safely. For installation, an arbor press is heavily preferred. It gives you that brutal yet perfectly even and controlled force you need for tight fits. For removal, bearing pullers like claw pullers are completely essential. Just make sure the claws of your pullers are free from burrs and kept in top condition so they grip smoothly. Oh, and you'll definitely need lifting gear and slings for the really large, heavy bearings, along with specialized hook and impact spanners for any adapter sleeve nuts. Sometimes a fit is just too tight for a cold press, so we have to use thermal expansion. Now, traditionally, engineers used to dunk bearings in a hot oil bath. But these days, modern induction heaters are the gold standard. They use electromagnetic induction to heat the metal super rapidly. They're massively cleaner, way easier to use, and they completely eliminate the risk of contaminating your pristine bearing with dirty oil before it even goes into the housing. And finally, Section 5, Precision Mounting Procedures. This is where all the theory, the tolerances, and the specialized tools finally come together. For smaller bearings, so generally anything with a bore of 100 millimeters or less, we go with a cold mounting procedure. Step 1 is always a meticulous inspection of the housing and shaft. You're looking for absolutely any burrs, nicks, or scratches. Then you apply a really light lubrication to the bearing seat, the journal, and the housing. It makes the drive-up procedure so much easier. You should also lightly lubricate the threads of any shaft nuts to minimize resistance. And remember, all sealed and shielded bearings must be mounted cold, no exceptions. But what happens when you're dealing with massive industrial bearings, especially ones on tapered bore shafts? Cold pressing with mechanical tools just isn't physically viable anymore. In these heavy-duty setups, engineers rely on oil injection combined with hydraulic nuts. Basically, this forces a micro-thin film of oil right between the mating surfaces, temporarily expanding that inner ring and drastically dropping the friction. That lets the hydraulic nut smoothly push the massive bearing into its precise position. Now, for really tight cylindrical bores, or large tapered bearings where you aren't using oil injection, you have to hot mount them. By heating the bearing to roughly 80 to 90 degrees Celsius above the ambient temperature of the shaft, the internal bore of the bearing physically expands. This lets the engineer swiftly slide the hot bearing onto the shaft, and as it cools down, it shrinks right back to its normal size, locking into an incredibly tight interference fit. But there is a hard physical limit to this thermal magic, and that magic number, 125. When hot mounting, you must never, ever heat the bearing to more than 125 degrees Celsius, which is about 260 degrees Fahrenheit. Pushing the temperature beyond this strict threshold actually alters the metallurgical properties of that specially hardened steel. You'll destroy its load-carrying capacity and completely ruin the bearing before it's even managed a single rotation. So think about it. You've selected the perfect bearing, you've respected the tolerances, maintained surgical cleanliness, and executed a flawless mount without exceeding any thermal limits. But honestly, the true test is just beginning. Because once that machine fires up and starts spinning, immense dynamic loads take over. Will you be able to recognize the subtle, invisible symptoms of an impending failure before it brings the entire factory grinding to a halt? Well, that dives into failure diagnostics, things like spotting a 10-degree temperature spike, or weird noise patterns, or diagnosing things like spalling and true brinelling. And that is a whole other beast we'll have to explore in our next explainer. Thanks for joining me.